Hello children, I'm your teacher Sweta teacher here again, and today we will be discussing about the capacitors. Now what are the things that we are going to do for today is, when we'll talk about capacitor, we'll talk about what is the basic function of the capacitor, we'll talk about its principle, then we are going to see that if we have got different capacitors, how we can arrange it into different forms, that is a series and parallel connection. And other than this, we are going to find out the capacitance of a conductor. We are going to find out what are the factors on which the capacitance is depending, and at the same time we'll see that what is the energy that is being stored in the capacitor. So today's class only for capacitors. Okay, so when we talk of capacitor, what exactly comes in our mind? So if you are asked what you mean by capacitor, the prompt answer that you should have to give that capacitor is a device which helps to store the charge. So capacitor is a device which will help you to store the charge. Now when we want the capacitor to store the charge, then what is the basic principle lying behind it so that we can store the charge? We have already seen that Q is proportional to V. That in the last class, one of the class, I had told you that if I want that the charge should be more, then what exactly is needed? The potential should be more. So the basic principle of the capacitor lies in this condition, that if we can increase the potential, then we can have more of the charges. It's very simple to understand that if we have got a device and if we want that more charge should be accumulated, then we have one factor responsible to do it, and that is what we are going to do with the potential. So let us see how things happens, how we do it. If we talk of a single conductor, a simple conductor, then it is when we talk of its capacitance, then let's see that if you take a single conductor and we talk of the capacitance, we have already done the case 4 pi epsilon 0 r when we were talking about the spherical conductor. So in that case, it was not giving you more of the charge to hold. Now at the same time, suppose if we take two conductors, suppose if we are taking two conductors and we just keep it separated by a distance. Okay, so let's see how things changes and how we can accommodate more and more charges. Okay, so let's start with that. We have taken two plates, and this plate we have given the charge. So it is the positive one. It is complete. By induction, the negative charge is being induced inside, right? So what we find that if we take two parallel plates, means you take two parallel plates, you take two spherical plates, you take two cylindrical plates, whatever be you take two plates, and one is given the positive charge, automatically induced negative charges there in the other side of the plates. Now what you really find that in this case the potential is decreased. Okay, in this case the potential is decreased by doing it up, and then you add more charge. But I want more charge, we want more charge to be given. So what can be the other alternative? We just earth it. The outside it is full of positive, isn't it? So when we earth it, just earth it. When you are doing the earthings, then what you find that the potential is further decreased. Now in order to raise the potential, you give more charge. So the basic principle is that we have got a system in which we try to reduce the potential, and when the potential is reduced, to increase the potential, you give more charge. So this is what you have to find out different ways so that you can do with it, and at the same time by doing this this is a very simple configuration for the capacitors, in which we are given one of the plate is given the charge, the other one is earthed, and this serves as a capacitor, a very simple basic capacitors, and then it helps you to store more and more charge, because when we do it, the system reduces the potential and you give more charge so that the potential is raised. So this way we are building we are building space so that we can accommodate more and more and more and more charge, right? So this becomes very significant for a capacitor. This is the basic principle for the capacitor, and we will have an equation when we will have a mathematical relation for the capacitance of a conductor, parallel plate capacitor, and then we'll come across with certain very important things once we derive the relation. So let us derive a relation for the capacitance of a capacitor. So we will basically take a very simple capacitor. We are going to take a parallel plate capacitor. Let us assume this is what we have. This is a parallel plate capacitor because there are two plates, plate 1 and plate 2. So let's assume that this is plate 1 and this is plate 2. Okay, so this is with the positive charge, the other one is with the negative charge. That is the basic things. Okay, so here what you find that if I take want to find out the electric field at the center for one plate, according to Gauss's theorem, electric field is what? Sigma by 2 epsilon naught. The distance between the two plates we have taken as d. Small d is what? Distance between the plates. Small d is the distance between the plates. Capital A is the area of the plate. Area of the plate. This area. Okay. So what we have taken, we have to find out the electric field at the in between. So in order to find out, we know from Gauss's theorem for one plate it is sigma by 2 epsilon naught. For if I take this position inside, it is to outward because positive, and since it is negative, it's towards negative. So what we find at the resultant electric field that we get here, E is equals to sigma by epsilon naught, because sigma by 2 epsilon naught plus sigma by 2 epsilon naught gives sigma by epsilon naught. Sigma is what? Surface charge density, and this is equals to Q by A. We know this. This is the charge by the area, right? What is our intention? We need to find out the capacitance, right? Now C is equals to Q by V. So we know we need to find out the potential, and how to find out the potential here? Here we have got electric field and the distance of separation between the two plates is what? D. So in order to find out V, we have got E is equals to V into D. Okay, or sorry, we have got E is equals to dV by dr. So V is equals to E into D. Right. So what we are getting up? E into D. So E is what? Sigma by epsilon naught into D. This is sigma by epsilon naught, and this is your D, right? I'll just wrap this side so that I can write. So sigma is what? Q by epsilon. So we have got V is equals to Q by A epsilon naught into D. So let us substitute in the final equation. C is equals to Q by V. So this is Q divided by V. So this is Q divided by V. What we had got for V, we have got Q D by A epsilon naught. So Q is cancelled out. This is A epsilon naught by D. This is the value of the charge. This is the value of the capacitance of the capacitor. So once you see the value, the capacitance of a capacitor depends upon what are the factors. It is not depending upon the charge. It is not depending upon the potential. It just depends upon the area, and it depends upon the distance between the two plates. If you put these plates to very close, then what you find that the capacitance is enhancing, means you are increasing the capacitance. If you take the area of the plate more and more, the surface area is more. So what you really find that here the value of A increases, the capacitance increases. The other factor is epsilon naught. For this category, we are doing the case today when we are not taking any dielectric material, but when we take the dielectric material, things changes. We'll have to think different way. Okay, because that becomes another factor to enhance again the ability to store more and more charge, or quench a thirst to have a capacitor which can give us lots of charge storing capacity. And since we are looking for a capacitor with lots of spaces for the charge so that maximum charge can be stored into it, so we look for all different alternatives so we can have some of the other ways, factors on which the capacitance of a capacitor depends. So first thing, very important, for few points you need to know that the capacitance of a capacitor does not depend upon the charge and the potential. First thing, very simple to understand. Second thing, it is not depending upon the size or shape or something like that. whatever shape or size you take, but you have to make it mandatory that one is given the charge, the other one is being earthed, and you keep a very separable distance between the two. So that the capacitance depends only upon the area of the plate and depends upon the distance between the plates. If the distance is less, the capacitance is more. So that is the basic formula that we did for the capacitance of a capacitor. Till now, I think you must be very much getting well acquainted with the capacitor. Now next, let's just with the capacitor. Let's suppose we have got a different set of capacitor and we look for a different arrangement of the capacitor. That is, we are going to look for a series as well as the parallel. So let's see how things changes there, how the capacitance changes when we do such combinations. First we are going to do with the series. So let's take, this is one capacitor, this is another capacitor, and this is another capacitor. This is given a charge and the other one needs to be earthed. Okay, this is the potential between the two plates. This is V2 is the potential between the two plates. V3 is the potential between the two plates, right? And they are well connected. So it is plus Q1 and this is plus Q2. This is plus Q3 for this, and this is minus Q1, minus Q2, and this is minus Q3. So we have got a system of 3 plates, and here the capacitance I'll take C1, for this I'll take C2, and here it is C3. That is what. It is given the positive charge, so this is positive, the other one negative, this is positive, the negative, the positive, and the negative. So they are connected in series, and they have the individual potential difference V1, V2, V3. Now we have got the complete, the equivalent potential as equals to V1 plus V2 plus V3, right? Now V is what? Q by C. C is what? C is the equivalent capacitance. And this is Q by C1 because charge is same. Charge flow is same. Okay, so Q by C1 plus Q by C2 plus Q by C3. So basically we are getting 1 by C, 1 by C1 plus 1 by C2 plus 1 by C3. So this is the condition when they are connected in series. Okay, so when they are connected in series, the equivalent potential is equals to 1 by C1 plus 1 by C2 plus 1 by C3, so on. Let's see what happens when they are connected in parallel. So we have one capacitor, this is another capacitor, this is another capacitor, this is connected, all the positive ends here, the negative ends here, positive, negative, positive, negative, Q1 minus Q1, Q2, Q2, Q3, Q3, and this is connected to the positive and this is being purged. So basic mechanism. And since we have got only 2 points for the capacitor, first is connected to the positive, here also connected, all positive at one end, all negative at one end, so we have got a common potential. So here the potential is same, when they are connected in parallel, potential difference is same. But charges are different, they will not have the same charge. The charge will be different. Since the charges are different, already C1 this has the capacitance C1, C2 and C3. So we will have Q as equals to Q1 plus Q2 plus Q3. Now since Q is equals to Q1 plus Q2 plus Q3, so we can write CV as the C becomes the equivalent capacitance. V is the potential difference. The potential is same, so it is C1V, C2V plus C3V. So what we get C is equals to C1 plus C2 plus C3. So you see that when You will do with electricity already. You know basic things about the electricity. When they were connected in series, the resistance was increasing, but here just the opposite. When they are connected in series, we see that the equivalent capacitance is decreased because it is the reciprocal of individual one. But when they are connected in parallel, the capacitance is increasing, right? So I hope today's class you have learned about the capacitor. You learned the basic mechanism of the capacitor. You learned how we can arrange the capacitor. You have learned what are the factors on which the capacitance of a capacitor depends, and the very important things that you need to know is about the energy. The energy is almost same. It will be the formula half CV square as we did earlier. Okay, so please go through things once again clearly, so that in the next class when we introduce dielectric, you should be well confident, well prepared to understand this. Thank you.